So let's explore a similar looking reaction here. We looked previously at hydroxide and methyl bromide. Now let's take a look at a reaction, like I said, is similar here. So we have methyl chloride. We'll do this in green. This is methyl chloride, and we're going to react it with methanol, or methoxide in this case. And it turns out that this proceeds by a very, very similar chemical reaction. That is, you're going to find out that it's a second order substitution reaction. So one thing's going to come in, the other thing's going to basically go away in this case. And one thing, just for trivial purposes here, we're not going to focus too much on the product here, but you'll notice here that in this particular reaction, you're actually forming an ether. Where does the ether portion come from? This is where it gets kind of cool. So if we kind of color this in here, and we color this in here, you can kind of think about this as sort of being like, this is the blue fragment that was right there. This is the green fragment that was right there. So they basically came together to form this brand new carbon-oxygen bond here. Okay, so the kinetics of this, since we know it's a second order process, or we're told that it's a second order process, is telling us that the rate is equal to a constant K times the concentration of methyl chloride times the concentration of methoxide. Okay, all we need to know is that if we want to make a prediction about the reaction rate, we have to pay very close attention to what's in here. That's it. That's all we have to focus on here. So let's see what happens as we start to vary these different, or we start to change these variables a little bit here. Now, keep in mind, we're going to do this as a relative. We're going to reference this to a reaction where we have 1 molar of the green, 1 molar of the blue. That's our kind of our baseline right there. Okay, so everything is in reference to that. So let's look at our first example here. We are going to increase in our concentration of methyl chloride. So what does that mean? Well, let's look at our rate law for a second. We are going to increase in the concentration of, I guess we should keep the colors constant, concentration of methyl chloride, right? So what's going to happen to the rate? Well, what have we learned for a second order process? As I increase in the concentration of methyl chloride, according to the rate law, as this number gets bigger, what happens to my rate? It should also increase here. So as we increase in the concentration of ClCH3, we should see an increase in the reaction rate. Why? Because according to the rate law, the rate is proportional to the concentration of ClCH3. All right, so we increase one, we increase the other one. Okay, let's look at the next example here. Wipe this out really quickly. We'll come back to our rate law. We'll put a little star by our rate law because that's kind of the star of the show and these problems here. All right, we're going to decrease the concentration of, it says HO minus, but this is important here. What happens if I decrease the concentration of HO minus? Is there any HO minus that's actually in the reaction rate or in the rate constant? Rate law. Let's try that again. Is there any hydroxide that's in the rate law? Well, look at what the rate law says. The rate law says it's K, it's equal to K times the concentration of methyl chloride plus, what is it, methoxide, right? So is there any hydroxide that's in that rate law? No. So what is hydroxide actually going to do to the rate of the chemical reaction? Absolutely nothing. Why? It's not in the rate law. No effect on the chemical reaction at all. It's not in the rate law. If it's not in the rate law, we don't care about it. Okay, what happens if I increase the reaction temperature? Want to take a guess? Say you have a little kid, right? Maybe you do, maybe don't, I don't know. Maybe babysitting a little kid, and kid's got a messy room. And you walk in and you go, hey buddy, you got to clean up your room. And they go, okay, yeah, I'll do it. And then 5 minutes later, you come back down to their room, and that hasn't been cleaned up yet. And you're like, all right, let's go. I asked you to do it. Come on, man, let's go. Turning up the heat a little bit, right? And so they go, oh, I'll get to it, right? And then 5 minutes later, you go back to the room, nothing's happened at all. And then this is where you just really crank the heat up, right? You go, let's go, get your act together, man. And what happens to the reaction rate now? The kid gets scared, right? Maybe, let's say. But the point is that you've increased the temperature. So what should happen to the cleaning up of the room? It should go faster. Exactly, right? We are increasing in the reaction temperature. So what's going to happen to the chemical reaction? We should see an increase in it. Yep. So as we increase in temperature, we should see an increase in reaction rate. Right, that's the hallmark of kinetics. And by the way, an extension of that is if you've ever gone to like Olive Garden before and they feed you way too much food there, you have leftovers, and you get home with your leftovers, where do you put the leftovers when you're done? In the refrigerator. Why do we put them in the refrigerator? Not to make them cold, but temperature, when we drop the temperature, it slows down the spoiling process. That's literally the reason why we do this. If you leave it on your counter, things spoil pretty quickly, but if you cool them down in your refrigerator, they tend to slow that process down. See, kinetics is actually applicable. What if we have our chemical reaction here and we add some Br minus to it? We add some bromide to it. What do you think is going to happen now? Well, look at the rate. What is the rate law telling us? What are the only things we need to focus on when we're talking about the rate? Methyl chloride and methoxide. Sorry, I keep saying hydroxide. It's methoxide. Is Br minus in that? So what does that tell us? Has no effect on it whatsoever. That's the point. Br minus is not in the rate law. No effect. And this is how we like to think about reaction kinetics from a really simple perspective.